Welcome to the deep dive. Today we're tackling a topic that is, well, absolutely non-negotiable if you're responsible for identity and access management, securing Keycloak.
That's right. I mean, just think about it. Keycloak sits right in the middle, controlling access to potentially all your applications, all your data.
hmm
It's the main gatekeeper.
Yeah,
And if that gatekeeper gets compromised, the impact is just catastrophic, right? It hits every connected service, every single user. So, yeah, understanding how to really lock it down is paramount.
exactly. And our mission today really is to take the stack of sources you've shared, and we've got some good stuff here. Specifics from the Red Hat build of Keycloak docs, foundational web app security principles from OWASP, the Open Web Application Security Project,
Mm.
and also some really practical security concepts about actually deploying applications, especially drawing from Kubernetes documentation.
Yeah, we're going to try and pull these different views together. So Keycloak's own security features, the kind of general web security challenges it bumps up against, and then the whole infrastructure side of things when you're actually running it.
Right.
It's kind of like looking at securing a building. You look at the locks and the doors, you look at the security policies for who gets in, and you look at the actual structural integrity of the foundation. All pieces matter.
Totally. And our goal here isn't just to list features. We want to dig in and pull out the really crucial insights, define the key security risks these sources are flagging, and then lay out exactly how to mitigate them based strictly on this material we have in front of us. We want you to walk away feeling, genuinely well-informed about securing this critical system.
It's definitely a multi-layered approach. You really need to pay attention to each layer because skipping one can seriously undermine the others.
Okay, so let's unpack this. Let's start at the core. The Keycloak layer itself, the configurations and the features inside Keycloak that are just essential for security.
Makes sense. Start with the heart of it.
As you said, Keycloak is the heart. It's handling authentication, authorization, tokens, everything. The sources are really clear. If an attacker gets unauthorized access or somehow takes control of Keycloak, they could potentially just bypass security for all the applications connected to it.
Yeah, it's the central point of trust.
Yeah.
Any weakness there just ripples outwards, potentially weakening your entire digital setup.
So, diving into the specifics then, the sources spend a good amount of time on the core protocols Keycloak uses, OAuth 2.0 and OpenID Connect. They flag specific risks and talk about how Keycloak, or your setup, should handle them. One that jumps right out from RC 9700 and the Keycloak docs is this risk of authorization code injection.
Right. Yeah, that's a tricky one. This is basically where an attacker manages to get their hands on a valid authorization code, maybe intercepts it, maybe finds it logged somewhere, and then they try to swap it for tokens like access tokens or ID tokens, pretending to be the legitimate client application.
How does that even happen? The sources mention a couple of ways, it seems. Like, an attacker might register their own malicious client app with Keycloak, but here's the sneaky part. They configure it to use a legitimate redirect URI that actually belongs to the target application.
Or, yeah, they might just try to reuse a code they observed from watching a legitimate user's login flow.
Okay, so how does Keycloak fight this?
Well, Keycloak, particularly the Red Hat build mentioned in the sources, helps out quite a bit through its compliance with the OS 2.1 authorization framework draft. The Keycloak server itself enforces a lot of the critical requirements from that spec, like really importantly, validating the redirection during the token exchange step. That helps tie the code back to the specific client and the redirect URI used in that initial request.
Okay, but here's a nuance that seemed really critical in the sources. While the Keycloak server side is doing the heavy lifting on 2.1 compliance, the Keycloak adapters, the libraries you put in your actual applications, they don't have specific OF 2.1 support explicitly called out in the docs we looked at,
Mm-hmm. That's a key point.
which seems to imply that some validations that maybe should happen on the client side, according to the spec, might still be on you to implement manually in your app code, or maybe rely on other libraries for. You can't just assume the adapter's doing absolutely everything, right?
Exactly. You need to be aware of that potential gap.
Yeah.
Now, one specific Keycloak adapter feature mentioned as a defense is the use nonce option. It's in the adapter's init configuration, and it defaults to true, which is good.
The nonce, like a number used once.
Yeah, basically, it adds a unique, cryptographically secure value, the nonce, to the initial authentication request. When Keycloak sends the response back after login, it includes this same nonce. The client adapter then checks, does the nonce in this response match the one I originally sent out?
Ah, okay, so it's like a secret handshake for that specific request instance.
Pretty much. It helps the client make sure that the response it just received really belongs to the specific request it initiated. on that specific device or browser instance. This makes it much harder for an attacker who snagged a code somewhere else to use it successfully from a different browser or location, because they wouldn't know the right nonce value for that original request.
Makes sense. But the sources, especially RFC 9700, pointed out a potential conflict here. Something about using the nonce in the redirect URI itself.
Yeah, it's an interesting edge case. Using the nonce within the redirection specifically for device or instance binding, while it sounds useful, could potentially clash with a requirement for the authorization server, Keycloak in this case, to strictly enforce exact matching of the redirector during that crucial token exchange step.
Wait, why would that conflict? And isn't exact matching super important anyway?
Oh, it's absolutely vital. Exact redirectory matching at the token exchange is a primary defense against code injection. The conflict arises if the redirectory used in the initial authorization request includes the nonce, maybe as a query parameter, making it unique for every single request.
Okay.
Now, if the server then only validates the base part of the URI at the token exchange step and not the full URI, including that unique nonce, or worse, if some providers, as the RFC notes, sometimes get lazy and just ignore the redirectory check at token exchange altogether, even though the spec says they shouldn't.
Then the attacker who has the code might still be able to exchange it even without knowing the nonce because that strict full URI match wasn't enforced when it mattered most.
Exactly right. So it highlights that while use nonce is a good feature, it's not like a magic bullet. The server's strict enforcement of the full redirectory match during token exchange is absolutely paramount. Which brings us directly to the next critical point, configuring your valid redirect URIs correctly in Keycloak in the first place.
This feels like one of the single most important security settings for any OAuth or OIDC client you register in Keycloak. Its main job, as the sources really hammer home, is to stop attackers from finishing a login flow and having Keycloak send the user, or worse, tokens directly in older, less secure flows to a malicious site the attacker controls.
And the Keycloak documentation is very specific about how you configure this. Wildcard values are allowed, but only at the very end of a URL pattern. So something like http.myapp.com/callback is okay.
But not http.myapp.com/com/callback?
Correct. Those are not allowed. And the reason for that restriction is simple but really powerful. If you could just stick wildcards anywhere, an attacker could potentially register a redirect URI that looks legit but points somewhere else, maybe like http.myapp.com.evil.com callback or http.myapp.com evil-path. If your pattern was too broad, it might match and they could trick users, get them redirected, and steal codes or tokens.
Restricting the wildcard to the end forces them to target a specific known base path, making it much harder to craft those malicious matching URLs.
Precisely. It limits their options significantly.
Okay, let's also touch on the response mode setting. This is in the adapter's init options too, right? Controlling how OIDC parameters get back to the client after login. The options are query or fragment.
Yep, query means parameters in the URL, fragment means after the hashtag.
And the sources make a really clear recommendation here. The default value, fragment, is generally safer, and the one you should stick with unless you have a very specific reason not to.
The security reasoning ties back to a general web security principle about the refer HTTP header. You see, parameters that are in the URL fragment after the hashtag are not sent to the server in the refer header when a user clicks a link on that page that goes to an external site.
But if you use query mode, those parameters are in the standard query string after the URL, and that query string often is included in the refer header when navigating away.
Right. So using fragment significantly cuts down the risk of accidentally leaking potentially sensitive OIDC parameters, like maybe parts of a code or state parameter, to third-party websites if a user happens to click an outbound link right after logging in. It's a simple config choice with a direct security benefit against information leakage.
And this whole idea of sensitive data leaking via URLs, it connects to broader web security stuff discussed in the sources, especially from OAuth's CSRF guidance, that's cross-site request forgery, and the ASVS referrer policy requirements.
Yeah, OAuth's CSRF cheat sheet is pretty adamant. Don't transmit sensitive stuff like CSRF tokens and URLs. And definitely don't use GIDI requests for actions that change state. The risks are just too high. Think about it. That URL ends up in browser history, web server logs, maybe network monitoring tools.
And those referrer headers we just talked about.
Exactly. If you put sensitive session IDs or tokens in the URL, they just end up scattered in places that are likely much less secure than your application's memory or, say, secure HTTP-only cookies.
So the core mitigation from OS, use get-only for safe read-only operations. Use post, put, delete, etc. for anything that changes state, and keep sensitive data in the request body or secure cookies.
And the ASVS requirement, v3.4.5, adds a specific technical control. Applications should configure a refer policy HTTP response header. This header lets you tell the browser exactly what information, if any, from the current URL should be included in the refer header when the user navigates away.
Policies like no refer or same origin or strict origin when cross-origin can effectively prevent leakage of potentially sensitive URL paths or query parameters.
So the implication for Keycloak here is really twofold. First, any applications you build that use Keycloak tokens need to follow these principles. Don't stick tokens or session IDs in URLs. Second, Keycloak's own web interface is the login page, the account console, the admin console. They should also be configured to send a secure refer policy header themselves. This protects against leakage from those Keycloak pages if, say, an admin or user clicks an external link while logged in.
Makes sense. Protect data both going into Keycloak flows and coming out of Keycloak's own UI. The sources also briefly mentioned clickjacking protection using content security policy with frame ancestors or the older X-frame options. That's about stopping someone embedding the Keycloak login page in a malicious iframe, right?
Exactly. Standard web security hygiene that applies to Keycloak's UIs too.
Okay, shifting gears slightly. Let's move from the flows themselves to the clients that participate in these flows. The sources talk about different client types, and picking the right one seems like a fundamental security choice.
It really is. Keycloak mainly distinguishes between confidential clients and public clients. The source also mentions bearer only, but notes it's deprecated, so let's focus on confidential and public.
Okay, confidential clients are for server-side apps.
Right. Applications running on a secure server backend where you can actually keep a secret safe. Because the code and configuration are in a controlled environment, you can trust it with a client secret. When a confidential client needs tokens, like when exchanging an auth code, it authenticates itself to Keycloak using that secret. Keycloak trusts the secret as proof that it's the legitimate client.
And public clients are the opposite, for browsers or mobile apps.
Exactly. They're for applications running in environments where secrets just cannot be protected. Think browser-based JavaScript apps or native mobile apps. Since the code runs on the user's device, any secret you embed in it is basically discoverable by anyone who looks.
So a public client can't use a client secret to authenticate itself. Its security, like we talked about earlier, relies almost entirely on Keycloak strictly enforcing those valid redirect URIs. That's the main control ensuring tokens or codes only go back to the legitimate app instance.
And the crucial insight here, though it sounds simple, is vital. You must configure the client type based on the actual security capabilities of the client application's environment. Calling a browser app confidential and giving it a secret doesn't magically make it secure.
Right, because the secret isn't actually secret in the browser. You're still relying on the valid redirect URIs anyway, so just configure it as public and be clear about where the real security boundary lies.
Precisely. Now, for how clients actually prove their identity to Keycloak, not user authentication, but the client application itself, the sources mention client authentication methods and specifically highlight signed JWTs as a strong option, especially for confidential clients.
Instead of just sending a shared secret, the client creates a JSON Web Token, JWT, signs it with its own private key, and sends that signed JWT to Keycloak as its authentication credential.
Yeah, and Keycloak gets the JWT. It looks inside to find the client's ID and the key ID that identifies which key was used for signing. Then it looks up the client's registered public key corresponding to that kid and verifies the signature on the JWT.
And this is stronger than secrets because the private key never leaves the client, right? Nothing sensitive that could be easily intercepted and reused, like a static secret, is transmitted over the wire during the authentication itself.
Correct. Now, Keycloak gives you two main ways to tell it about the client's public key so it can do that verification. You can either configure a JWKS URL, that's a JSON Web Key Set URL,
Okay.
or you can directly upload a specific public key file or a certificate containing the public key into the Keycloak client configuration.
And the sources seem to lean towards using the JWKS URL as being more flexible, especially for key rotation.
Definitely. With a JWKS URL, Keycloak can dynamically fetch the client's public keys from that specified web endpoint whenever it needs them. So if the client rotates its signing keys and updates the key information published at its JWKS URL, Keycloak can automatically pick up the new public keys.
How does it know when to check?
Typically, it happens when Keycloak receives a signed JWT from the client that's signed with a key ID, KID, it hasn't seen before, or for which it doesn't have the public key cached. It then goes out to the registered JWKS URL for that client, downloads the latest set of keys, finds the one matching the kid, caches it, and verifies the signature.
Ah, so it's much more dynamic. Uploading the key or certificate directly means you have to manually go into Keycloak's admin console and update the configuration every single time the client rotates its keys.
Exactly. The JWKS URL approach makes key management much smoother from Keycloak's perspective, especially if you have many clients or rotate keys frequently.
All right, moving on to what information clients actually get inside the tokens and managing their access permissions. Client scopes and audience claims seem like really core Keycloak concepts here.
They are. Client scopes are essentially named bundles of configuration. They determine which protocol mappers and which role scope mappings get applied when Keycloak is issuing tokens for a specific client.
And those mappers and mappings are what actually populate the claims inside the access token and IED token, like user attributes, user roles, group memberships, and that audience odd claim.
Precisely. The sources differentiate between default client scopes and optional client scopes. Default scopes are, well, always applied to the token for that client no matter what. Optional scopes are only included if the client specifically asks for them using the scope parameter in the initial authorization request.
So this gives clients pretty fine-grained control over what's actually inside the tokens they receive.
It does. And the underlying security principle here, which the sources implicitly reinforce, is least privilege. You should only assign the default and optional scopes to a client that are absolutely necessary for that application to do its job. Don't just dump every possible user attribute or role into every token if the client doesn't actually need it. Minimize the data exposure.
Makes sense. Now, about that odd claim, the audience claim. It indicates who the token is intended for, usually a resource server. The source explained how client roles can play a part in adding a client ID to this claim.
Yeah, it's an interesting mechanism. If you assign specific client roles to a user, roles defined within a specific client's namespace in Keycloak, and then you configure a role scope mapping on a client scope to include those client roles in the token, you can often configure that mapping such that the client ID associated with those roles gets added to the odd claim.
Okay, let's walk through an example. Say I have a back-end API, Service 1, registered as a client in Keycloak.
Yeah.
And I have a front-end app, also a client. I want tokens issued to the front-end app intended for Service 1 to have Service 1 in the odd claim.
Right. So you could create a client role within the Service 1 client, maybe called API user. You'd assign this Service 1 API user role to the users who should be allowed to call the API.
Okay.
Then you'd create a client scope, maybe called API access scope. On this scope, you'd add a role scope mapping for user-client roles. You'd configure this mapping to specifically look for roles associated with the Service 1 client, and importantly, configure it to add the Service 1 client ID to the odd claim if the user has such a role.
Got it. And then I'd assign this API access scope to my front-end client, maybe as an optional scope that the front-end requests when it needs to call the API.
Exactly. Or if the front end always needs to call that API, you could make API access scope a default scope for the front end client. The sources also mention you could potentially add that specific role mapping directly to the front end client's own dedicated client scope if you prefer.
But here's a really crucial detail the sources pointed out. This whole mechanism relies on the user actually having a client role for that target service, right?
Absolutely critical point.
Yeah.
If the user whose token is being generated doesn't have any client roles assigned for Service 1, in our example, they don't have the Service 1 by user role, then Service 1 will not be added to the odd claim using this role mapping method, even if the scope is configured correctly and is requested or default.
That's a really important catch. It means you can't solely rely on this client role mapping approach to guarantee an audience claim is always present for a specific service unless you're certain all relevant users will have the necessary client role for that service. You might need other ways to ensure audience, perhaps protocol mappers configured differently depending on the use case.
Right. It's powerful, but has that dependency on user role assignments. Okay, let's move on to managing users and their sessions securely within Keycloak itself, starting with something absolutely fundamental, password storage.
Yeah, the OWASP password storage cheat sheet provides the gold standard here, the main principle. Even if an attacker steals your database, they shouldn't get plain text passwords. Ever. Hashing is the way.
And not just any hashing. OWASP stresses using algorithms that are deliberately slow and computationally expensive. Think algorithms like Argon2, Bcrypt, or Script. They're designed to make offline brute force attacks where the attacker has the hash list and tries billions of passwords incredibly time-consuming and costly.
The goal is to make it just impractical, right? So even with powerful hardware, cracking enough hashes to be useful would take years or decades. Keycloak handles this internally, using strong algorithms like PBKDF2 by default, but it's crucial for admins to understand why this is done and to stick with strong hashing providers if they ever customize Keycloak's setup.
Definitely. Now, user profiles and the attributes you define for them in Keycloak's admin console also have security implications.
The Keycloak docs point out that strictly defining and validating these attributes adds a layer of defense. By default, Keycloak seems to ignore any attributes sent during registration or profile updates that aren't explicitly defined in the realm's user profile configuration.
Which is good. You can configure attributes with a name, display name, and importantly, whether they're multi-valued. If an attribute can hold multiple values, like maybe multiple phone numbers, the sources say you must apply a validator to set a hard limit on how many values are allowed.
So that stops an attacker trying to maybe stuff thousands of values into an attribute field, potentially causing denial of service or exploiting some processing bug down the line.
Exactly. It's a simple but effective control against data stuffing attacks. You can also control when attributes are enabled or required. They can be always enabled, required, or, and this is quite powerful, their status can depend on whether specific scopes are requested.
Oh, interesting. So you could have a sensitive attribute, maybe like a national ID number, configured so it's only enabled or required for a user to provide if a client application specifically requests a scope, say KISAC6 scope, that actually needs that information.
Precisely. It allows you to dynamically enforce your data privacy and collection policies based on the context of the client application and the user's interaction, linking user data management directly back to that client scope strategy we discussed earlier.
And the fine-grained permission settings for each attribute seem key too. You can set read and write permissions separately for the user when the end user is looking at or editing their own profile, and for the admin when an administrator is managing the user via the admin console.
Yeah, that's essential for controlling who sees what and who can change what. You don't want users modifying critical attributes themselves, and maybe only certain admin roles should be able to view highly sensitive PII.
Okay, let's talk session management settings within Keycloak. These seem critical for security posture.
Absolutely. Keycloak offers several relevant timeouts and settings. There's Client Session Max, which dictates how long a client session can be active, essentially governing the refresh token expiry. This should generally be shorter than the main SSO session max, the overall single sign-on session lifetime.
Right. And offline session idle, that's for those long-lived offline tokens used by services that need access when the user isn't present.
Exactly. It sets an idle timeout for them. Then there's failure reset time, which controls how long Keycloak remembers failed login attempts for a user before resetting the counter. This needs to be carefully balanced with the max wait setting for temporary lockouts to prevent attackers from easily enumerating users or brute forcing passwords by just waiting out the reset timer.
Connecting this to broader principles, OWASP's session management cheat sheet has some general best practices that apply here too. They strongly recommend securing session IDs, particularly preferring secure HTTP-only cookies over putting session IDs in URL parameters to prevent session fixation attacks.
Session fixation is where an attacker tricks a user into starting a session with a session ID the attacker already knows, right?
Yeah.
Then when the user logs in, the attacker can hijack the session.
Exactly. Cookies help prevent that. OS also suggests giving users themselves more visibility and control over their sessions. Things like letting users see a list of their currently active sessions across different devices or browsers. Maybe getting alerted if someone logs into their account from a new location, concurrent logins, having the ability to remotely terminate sessions they don't recognize.
Yeah, like a log out everywhere button.
Right. And maybe seeing a history of their login activity, IP address, browser type timestamps. While Keycloak manages the core session mechanics, exposing these kinds of features in the user's account console really leverages that capability to empower users and help them spot suspicious activity.
Definitely enhances user security awareness. Now, multi-factor authentication, MFA, obviously a huge defense layer. Keycloak supports several methods. For OTP, the classic time-based one-time passwords from authenticator apps.
Like Google Authenticator or Authy.
Exactly. Keycloak has settings like number of digits, usually 6, but longer could be slightly more secure, maybe slightly less user-friendly. And look around window, which is important. It allows for a bit of clock drift, maybe a few seconds or a minute, between the server's clock and the user's phone clock, so that the code is still accepted even if they're not perfectly synchronized.
Okay. And for WebAuthn, that's the standard for security keys like YubiKeys, and also platform authenticators like Windows Hello or Touch ID Face ID. And now passkeys.
Right. Admins can manage these credentials. You can set the WebAuthn register required action to prompt users to set one up during login. Admins can see some basic data about registered authenticators, delete them if a user loses a key, or add labels to help users identify them.
And if you want to go full passwordless using WebAuthn,
For true passwordless login, where the user doesn't enter a password at all, specific policy settings in Keycloak are crucial. You need to set the user verification requirement to required. This means the authenticator itself must verify the user is present, usually via a fingerprint, face scan, or a PN entered on the security key itself.
okay.
And you also need to set required discoverable credential to This means the authenticator must store the credential on the device. These are sometimes called resident keys, or more commonly now, passkeys, so the user can initiate login just by interacting with the authenticator without needing to type a username first.
But the sources mention a limitation here, something about mixing policies.
Yeah, a potentially tricky point. The sources note that Keycloak currently lacks a dedicated separate policy specifically for passwordless scenarios. This makes it difficult within a single realm policy to easily mix different WebAuthn requirements. For example, it's hard to say these users require user verification, but these don't, or these users must use discoverable credentials, while these can use non-discoverable ones, all within the same login flow governed by one policy.
So you might need separate realms or more complex authentication flows if you have diverse WebAuthn needs. And there was a mention of storage limits.
Right. Physical security keys, especially older ones, have limited storage capacity for discoverable credentials, passkeys. So a user might hit a limit on how many passwordless logins they can register on a single key. Newer keys and platform authenticators generally have more capacity.
Good points. Okay, one last area within the Keycloak application layer itself, securing access to Keycloak's own administrative interfaces and APIs.
This is critical. And the Keycloak docs have a stark warning about how built-in admin roles interact with fine-grained permissions. Here's the key takeaway. If you assign one of Keycloak's built-in administrative roles, like admin in the master realm or realm admin in another realm, to a user, that assignment completely bypasses the evaluation of any fine-grained permissions you might have painstakingly configured for that user on specific resources.
Whoa, really? So if someone has the realm admin role, they get full access to everything in that realm, even if I tried to use fine-grained permissions to restrict their access to, say, only manage users but not clients.
That's exactly what the sources state. The broad built-in admin role takes precedence and effectively grants full privileges for its scope, ignoring the more specific permission policies.
That is huge. It really underscores that you need to be extremely cautious about granting those broad, built-in admin roles. Prefer using more specific roles you define yourself, or rely on fine-grained permissions where possible, though the sources do clarify that you cannot use fine-grained permissions to override the access granted by the default built-in admin roles.
Right. Use those powerful built-in roles very, very sparingly. Now, the client registration CLI, KULDM.esh, it's a handy tool for scripting and automation.
But it has a local security risk?
Potentially, yes.
Yeah.
By default, it can store configuration, including potentially sensitive access tokens or client secrets needed to talk to Keycloak's admin API, in a properties file, usually .kdm.properties.
So if that file isn't protected properly, another user on the same system could potentially read it and grab those credentials.
Exactly. The mitigation is straightforward but essential. Make sure that configuration file has restricted file permissions, readable, writable only by the owner. For maximum security paranoia, the sources suggest using the no config option every time you run ktdm.esh.
That sounds less convenient, though.
It is. It means you'd have to re-authenticate or provide credentials tokens via command line arguments or environment variables for every single indication. But it completely avoids storing any secrets persistently on the file system via that config file. It's a trade-off between convenience and security posture.
Got it. And the sources also mentioned initial access tokens. What are those for?
These are special, short-lived tokens created by a realm administrator. They're specifically designed to allow developers or automated systems to perform initial client registration via the API without needing a full Keycloak user account with admin privileges.
Ah, okay. So you generate one of these tokens, give it to a developer or a CI/CD pipeline.
Right, and the realm admin controls the security of these tokens by setting their maximum age, how long they're valid for, and importantly, the maximum number of clients that can be registered using that single token. Once the count or the expiry time is reached, the token becomes useless.
So the security relies on the admin managing these tokens carefully, short lifespans, low usage counts, only giving them to trusted parties or processes. Wow, okay. We have really dug deep into the guts of Keycloak's own security configurations and how they tie back to general web app principles, all based on these sources.
Yeah, but like we said at the start, just configuring Keycloak itself isn't the whole story, is it?
Yeah.
You absolutely have to consider the environment it's actually running in.
Exactly. And this is where those principles from OWASP SVS and the Kubernetes documentation become so critical. Let's shift focus now to the deployment layer security.
Makes sense. Foundation first. And a core foundation, heavily emphasized in OWASP ASVS v12.3, is securing all network communication. The requirement is crystal clear. WU's encrypted protocol, which almost always means TLS for all network connections, period.
And they mean all connections, right? Both inbound to Keycloak from clients or users and outbound from Keycloak to other systems.
Everything. Keycloak talking to its database, talking to LDAPs or Active Directory, calling external APIs, receiving connections from your front-end apps, even connections from your monitoring tools, management consoles, or remote access like SSH into the server running Keycloak. All of it needs encryption.
And a really critical rule that accompanies this. The server must not fall back to insecure or unencrypted protocols if the secure TLS connection attempt fails. If TLS negotiation breaks down, the connection should just terminate. No downgrading to plain text allowed.
ASVS v12.3.2 adds another piece. TLS clients must validate the certificates they receive before starting communication. So when Keycloak acts as a client connecting out to, say, a database or an LDLS server, it must validate the certificate presented by that server.
And similarly, applications connecting to Keycloak must validate Keycloak's TLS certificate, no just blindly trusting certificates.
And v12.3.3 takes it even further internally. It requires TLS or another appropriate transport encryption mechanism for all connectivity between internal HTTP-based services within your application architecture. So if your Keycloak deployment relies on talking to other internal microservices or APIs over HTTP, that internal traffic must also be encrypted. No exceptions, no fallback. This TLS everywhere principle is really a cornerstone of a secure deployment environment.
Okay, now often Keycloak isn't directly exposed to the internet, right? It runs behind a load balancer or a reverse proxy, and that proxy often handles the TLS termination, meaning the encrypted connection from the user's browser ends at the proxy.
And then the proxy talks to Keycloak on the internal network, maybe over plaintext HTTP, or maybe it re-encrypts the traffic using TLS again for the connection to Keycloak. The Keycloak server configuration sources we looked at discuss how to handle this scenario securely.
Right. When TLS termination happens at the proxy, Keycloak needs to know the original client's IP address and the original protocol, HTTPS, to function correctly, especially for logging and generating correct URLs. This is usually passed via headers like xforwarded for and xforwarded proto.
And Keycloak needs to be configured to trust these headers, but only from the IP address of your trusted proxy servers. You don't want an attacker bypassing the proxy and sending forged headers directly to Keycloak.
The sources mention different proxy modes Keycloak supports, like re-encrypt, proxy decrypts, then re-encrypts to Keycloak, edge, proxy decrypts, talks plaintext to Keycloak, and pass-through. Proxy doesn't terminate TLS, just passes encrypted traffic through. They recommended pass-through if you need end-to-end X.509 client certificate authentication.
Yeah, because with pass-through, the TLS connection goes all the way to Keycloak, so Keycloak can handle the client certificate negotiation directly. This avoids passing sensitive client certificate information via potentially less secure HTTP headers from the proxy, which happens in re-encrypt or edge modes if you're doing client cert off that way.
Okay, but if you are using re-encrypt or edge mode and you are trying to pass client certificate information from the proxy to Keycloak via headers,
Right.
the sources laid out some mandatory security measures.
Absolutely critical ones. First, your network topology must be set up so that Keycloak is completely isolated and can only accept connections directly from your trusted proxy servers. No other client should be able to reach Keycloak directly on its HTTPS port. Otherwise, they could bypass the proxy and potentially inject forged headers.
Makes sense. Network isolation.
Second, the proxy must be configured to securely overwrite the specific HTTP header that Keycloak is configured to use for looking up the client certificate information. That's the SPIDAX 509 cert lookup provider SL client cert setting. The proxy must strip out any header with that name sent by the incoming client and insert its own validated information. An attacker shouldn't be able to just send their own forged header hoping Keycloak picks it up.
Okay, overrate the header. But here's the part that the sources flagged as a major risk regarding proxying and client certs. That SPY by 509 cert lookup provider trust proxy verification setting.
Oh yeah, This one is incredibly dangerous if misunderstood or misconfigured.
What does it do?
If you set trust proxy verification to true, you are telling Keycloak, trust the proxy completely. Assume that if the proxy passes along client certificate information in the header, the proxy has already fully validated the entire certificate chain against the necessary certificate authorities, CAs.
Okay, so Keycloak skips doing the validation itself.
Exactly. It trusts the proxy did it.
Mm-hmm.
Now, if you set this to true, but your proxy is not actually configured to perform that full, rigorous client certificate chain validation before it sets the header, you've just created a massive security hole.
Because an attacker could potentially forge a client certificate, maybe self-signed or signed by an untrusted CA, send it to the proxy. If the proxy isn't configured to validate it properly, it might just extract the subject info, put it in the header, and forward it to Keycloak. And since trust proxy verification is true,
Keycloak incorrectly assumes the certificate was valid and authenticates the client based on the forged credentials passed in the header. Boom! Unauthorized access.
wow. Okay, so the bottom line is, only set trust proxy verification true if you are absolutely certain your proxy is performing full client certificate chain validation against your required CAs. If the proxy isn't doing that full validation, this setting must be false, and Keycloak needs to perform the validation itself, which usually requires pass-through mode or careful configuration in re-encrypt.
Extremely critical point. Misconfiguring that is asking for trouble.
All right, shifting to a Kubernetes context now. If you're deploying Keycloak on K8s, network segmentation using Kubernetes network policy resources sounds like a really powerful tool.
It absolutely is. Network policy lets you define firewall rules at the pod level, controlling which pods can talk to which other pods and which pods can talk to external networks, egress, or receive traffic from outside the cluster, ingress. The key security benefit here is enabling a default deny posture.
How does that work in K8s? The default is usually allow all, isn't it?
It is, unfortunately, within a namespace. But you can change that. The Kubernetes docs show how. You create a network policy resource within the namespace where Keycloak runs. You set its pod selector to all pods, which means it applies to all pods in that namespace. Then you give it empty ingress and egress lists and specify policy types. Ingress, egress.
So a policy that applies to all pods but doesn't explicitly allow any traffic in or out?
Exactly. This policy by itself doesn't permit anything. It establishes the baseline. For all pods in this namespace, unless another network policy explicitly allows traffic to or from them, deny all ingress and egress.
That sounds much more secure than the default allow all. It forces you to think about and explicitly define only the network paths that are absolutely necessary for Keycloak to function.
Precisely. You then create other network policies to specifically allow, say, ingress traffic to the Keycloak pods from your front-end application pods, or an ingress controller, egress traffic from Keycloak pods to the database pods, maybe egress to an LDAC server outside the cluster. This dramatically limits the potential blast radius or lateral movement. If an attacker were to compromise one pod, they wouldn't be able to just scan and attack everything else in the namespace.
Okay, beyond networking, securing the data, Keycloak relies on credentials, realm secrets. Configuration is obviously vital. Let's look at securing data storage, especially in that K8's context again.
Right. If you're running Keycloak on Kubernetes, sensitive configuration data often ends up stored within Kubernetes itself, specifically in the etc. data store. This includes Kubernetes secrets used by your Keycloak pods, holding things like database passwords, initial admin credentials, or realm keys.
And maybe sensitive data in any custom resources if you're using a Keycloak operator to manage your deployment.
Potentially, yes. So protecting this data stored in etc. is important. The Kubernetes documentation provides a mechanism for this, encryption at rest for the Kubernetes API server. This encrypts the sensitive resource data before it gets written to, etc.
How do you set that up?
You configure it via an encryption configuration object, which is usually provided as a file to the kubeapp server. This configuration file specifies which Kubernetes resource types, like secrets, maybe config maps if they hold sensitive info, or specific custom resource definitions, should be encrypted, and which encryption provider to use. The main provider for actual encryption is AECBC, which uses AES in CBC mode with a key you provide. There's also an identity provider, which essentially means no encryption. It's mainly used as a fallback during the migration process to allow the API server to still read existing unencrypted data.
So the process is, create this config file with your keys and specify secrets under the ECBC provider, maybe list identity as a lower priority provider initially. Then you mount this file into the Cube App Observer pod, usually by editing its static pod manifest on the control plane nodes, and restart the API server.
Right. And verification is key here. After the API server restarts with the new configuration, any new secrets created or any existing secrets that get updated will be encrypted using ACBC before being written to, etc.
But existing secrets that aren't touched remain unencrypted.
Correct, until they are updated. To ensure all sensitive data is encrypted, you typically need to run a command to force a rewrite of all existing resources of the configured types. Example, kubectl get secrets all namespaces, sayo JSON, kubexl replace exefiashi.
And then, crucially, once you've confirmed all the target data is encrypted, you can check by trying to read it directly from etc. using etc. total. You must remove the identity provider from the encryption configuration and restart the API server again.
Yes. Removing the identity provider ensures that the API server will no longer honor or be able to read any unencrypted data for those resource types. This completes the process and protects against accidentally reading old, unencrypted backups or data. It protects the K8 stored config from being read if etc. is compromised. Though remember, this doesn't encrypt data inside Keycloak's own application database. That's a separate concern.
Okay. Now, within Kubernetes, the standard way to get sensitive config into your Keycloak pods is using Kubernetes secrets, right?
Exactly. Secrets are the K8's object type designed specifically for holding sensitive data like database credentials, TLS private keys for Keycloak's HTTPS endpoint, maybe Realm private keys, or initial admin passwords.
And how do the Keycloak pods actually use these secrets?
Two main ways. You can mount a secret as a data volume inside the pod. The keys within the secret then appear as individual files in a specified directory within the container's file system. Keycloak can then read these files. Or you can expose specific keys from a secret as environment variables directly to the Keycloak container.
Is one way better than the other?
Mounting as files is often preferred, especially for things like certificates or multi-line keys, as environment variables can sometimes have limitations or might accidentally get logged. Files also allow for automatic updates within the running container if the secret object is updated in Kubernetes, whereas environment variables are typically set only at container start time.
The docs mention that secret volume sources get validated.
Yeah, the kubelet checks with the API server when starting the pod to make sure the secret referenced in the pod spec actually exists, which leads to a dependency. The secret object must be created in Kubernetes before you try to start any pod that depends on mounting or using it.
And there was a small caution about using the string data field in secret manifests.
Right. String data lets you put plain text values directly in your YAML, which is convenient, but the docs noted it doesn't always play well with server-side apply, a common way to manage K8's resources. It's generally safer and more standard to use the data field and provide base64 encoded values for your secrets.
Okay. And for non-sensitive configuration, like maybe Keycloak theme settings or certain Realm config parameters that aren't secret, that's where config maps come in.
Exactly. Config maps are the K8's way to handle non-sensitive configuration data. They work very similarly to secrets in how they can be consumed by pods mounted as volumes, appearing as files, or exposed as environment variables. But they're intended for non-confidential information. They aren't encrypted at rest and etc. by default unless you explicitly add config maps to your API server encryption configuration.
Got it. Secrets for secrets, config maps for config. Now let's talk about securing the actual runtime behavior of the Keycloak containers within Kubernetes. The principle of least privilege seems absolutely fundamental here.
It is. You want to restrict the permissions granted to the process running inside the Keycloak container as much as possible. Kubernetes gives you tools for this via the pod security context and container security context.
One powerful tool mentioned was dropping Linux capabilities.
Yeah, the sources referenced a strong policy recommendation. Containers should drop all Linux capabilities by default, and then you only add back the absolute minimum capabilities that the application, Keycloak, genuinely needs to function.
What kind of capabilities might Keycloak need?
For a typical web server like Keycloak, if it needs to bind to a privileged port, like 80 or 443 ports below 1024, it might need the NetBind service capability, but it likely doesn't need capabilities related to changing network interfaces, mounting file systems, or changing system time. Dropping all unnecessary capabilities dramatically reduces the potential impact if the process inside the container gets compromised. The attacker simply won't have the privileges to do much damage to the underlying host system.
Another key control is running as a non-root user inside the container.
Absolutely. Explicitly configure your Keycloak container security context with run as non-root. True. This ensures the main keycloak process runs as an unprivileged user ID within the container's namespace. Even if an attacker finds an exploit in keycloak, escaping the container or gaining root privileges on the host node becomes much harder if the process isn't running as root inside the container to begin with.
The sources also mention user namespaces, host users, falls as a more advanced feature.
Right. This is a newer Linux kernel feature that K8 is starting to integrate. It allows a process to run as root, 1E0, within its own isolated user namespace inside the container, but that root user maps to a non-privileged regular user ID on the host system. It offers even stronger isolation between container UIDs, GIDs, and host UIDs, GIDs, but the sources noted it's still relatively early days and might lack support in some tools or environments.
Now, a really practical point with applying these least privileged controls running as non-root dropping capabilities, you have to make sure the specific user ID the container ends up running as actually has the necessary permissions inside the container image, right? Like permissions to write logs, read config files, bind to configured ports if above 1024.
Crucial point. Yes, if you build a container image where everything is owned by root and requires root privileges, then just tell Kubernetes to run it as non-root. It's likely going to fail immediately with permission-denied errors when Keycloak tries to write files or open sockets. You need to design your container image using US hero directives in the Docker file, setting appropriate file ownership and permissions. To work correctly when run as the intended non-root user, it requires careful testing.
Makes sense. Okay, resource limits and quotas. These seem vital for preventing denial of service dayless attacks, whether malicious or just accidental, both against Keycloak itself and the underlying K8's nodes.
Definitely. You don't want Keycloak falling over because it ran out of memory or bringing down the whole node with it. Kubernetes offers controls at multiple levels.
At the namespace level, there's resource quota.
Right. You create a resource quota object in the namespace where Keycloak runs. It lets you set limits on the total aggregate amount of CPU and memory requests and limits that can be consumed by all pods running in that namespace. You can also limit storage requests or even the total number of objects like pods or persistent volume claims allowed.
So this prevents Keycloak, or maybe some other misbehaving application in the same namespace, from hogging all the resources and starting other essential apps.
Exactly. It puts a ceiling on the namespace's total resource consumption.
And at the node level, there's node allocatable.
Yes, this is configured on the kubelet service, running on each worker node. It reserves a certain amount of CPU, memory, ephemeral storage, and PIDs specifically for the node's operating system processes and for the kubelet itself. These reserved resources are subtracted from the node's total capacity to determine the allocatable resources available for scheduling pods.
Ah, so this ensures the node itself remains stable and responsive, even if the pods running on it are using up all their allocated resources.
Precisely.
Hmm.
The kubelet enforces pod resource limits based on this allocatable capacity and can start evicting pods if the node comes under critical resource pressure, like running out of memory or disk space, to try and reclaim resources and keep the node alive.
PID limiting was also mentioned, preventing fork bombs.
Yeah, that's another kubelet configuration flag. Podmax PIDs or node-level settings to limit the total number of processes, PIDs, a pod can create. This helps prevent a single runaway pod from exhausting the node's process table and destabilizing the whole machine.
And the Kubernetes API server itself needs protection, especially if Keycloak is interacting with it heavily, maybe via an operator.
Right. The API server can become a bottleneck or DOS target. Kubernetes has a feature called API Priority and Fairness. It works by classifying incoming API requests using flow schemas, matching requests based on user, verb, resource, etc., assigning those requests to predefined or custom priority level configurations, which have separate concurrency limits, and then using fair queuing algorithms within each priority level to ensure that high volume or lower priority requests don't completely block important higher priority requests.
So it keeps the API server responsive even under heavy load.
That's the goal. It protects the control plane. And finally, kubelet eviction is the kubelet's last resort when a node is critically low on resources like memory, disk space, or inodes. It starts killing pods based on configured hard eviction thresholds and pod priorities to try and recover the node. The docs mentioned graceful node shutdown grace in peer by pod priority, also honors these priorities, trying to terminate critical pods like Keycloak last during planned node maintenance.
The bottom line for all this seems to be, you absolutely must apply appropriate resource requests, what a pod needs to run, and limits the maximum it's allowed to use to your Keycloak pods in Kubernetes. This is essential not just for scheduling, but for enabling all these stability and DOS protection mechanisms to actually work effectively.
Couldn't agree more. Skipping resource requests and limits is asking for instability.
Okay, image security. This seems crucial for supply chain integrity when deploying containerized apps like Keycloak. What's the main risk highlighted?
The primary risk discussed in the K8 stocks is relying on mutable image tags like keycloak.latest or even keycloak.18bonos.2. The problem is that the actual code or content associated with a specific tag in an image registry can change over time. The registry owner could push a new image with the same tag, maybe containing patches, maybe containing accidental changes, or maybe even containing malicious code if the registry build process is compromised.
So if you just deploy based on the tag keycloak.18bot0.2, you might pull and run a slightly different version today than you did yesterday without realizing it.
Exactly. You lose reproducibility and introduce uncertainty, potentially vulnerabilities.
So what's the mitigation?
Use the image digest instead of the tag in your Kubernetes pod manifests or Helm charts, etc. An image digest is a unique immutable cryptographic hash, usually SHA-256, of the image's content and configuration. It looks something like SHA-256.abcdec123. When you specify an image by its digest, Kubernetes pulls and runs that exact specific version of the image every single time.
Guaranteed reproducibility. It ensures you're always running the code you intended to run, regardless of any changes happening to tags in the registry.
Precisely. It's a simple change with a huge security benefit for supply chain integrity.
And if you're using private image registries to store your Keycloak image or maybe custom DARF images,
Securing access to those private registries is also important. Kubernetes provides mechanisms like image pool secrets, which contain registry credentials and can be associated with service accounts used by your pods. Alternatively, you can configure credentials directly on the nodes or use more advanced credential provider plugins for integrating with cloud provider registries or other systems.
okay, last area under the deployment layer, secure node configuration within Kubernetes. This is about the underlying worker machines. What are the key points?
One very practical operational risk is certificate expiry. All the TLS certificates used for communication between Kubernetes components, kubelet client certs, talking to the API server certs, etc., certs, they all have expiration dates. If they expire, things break badly. The sources mentioned using tools like QBM certs. Renew all if you used QBM to set up your cluster to manage certificate renewal. Regular monitoring of certificate expiry is crucial. Kubelet API security was also mentioned. Yeah, ensuring that the kubelet API itself, which runs on each node and controls pods on that node, requires proper authentication and authorization, is important to prevent unauthorized access or control over pods running on a node.
And finally, node isolation and restriction. This is about controlling where your sensitive Keycloak pods actually get scheduled within the cluster.
Exactly. You might not want your critical Keycloak instance running on the same nodes as potentially less trusted or experimental applications. You can use various Kubernetes scheduling features to enforce this.
How?
It usually starts with applying labels to your Kubernetes nodes, maybe security high or workload infra. Then, in your Keycloak deployment's pod specification, you use scheduling constraints.
Like node selector.
Node selector is the simple. It just says, only schedule this pod on nodes that have this specific label key value pair.
But there are more advanced options: affinity, anti-affinity, and taints tolerations.
Right. Node affinity, required during scheduling, ignored during execution, provides more expressive rules for required node selection, like matching multiple labels or using operators like exists or not in. Node anti-affinity lets you say, don't schedule this pod on nodes where pods with this label are already running, helping to spread critical workloads or keep conflicting ones apart.
And preferred during scheduling, ignored during execution is like a soft preference. Try and run here, but it's okay if you can't.
Exactly. Then you have taints and tolerations. A taint is applied to a node for G critical addon simile true, no schedule, and it acts like a repellent. The scheduler won't place any pod on that node unless the pod has a matching toleration in its spec.
So you can taint specific nodes to dedicate them for critical infrastructure like Keycloak, and only Keycloak pods with the matching toleration will be allowed to run there, or use taints to keep general workloads off those sensitive nodes.
Precisely. By combining labels, selectors, affinity rules, taints, and tolerations, you gain fine-grained control over ensuring your Keycloak deployment lands only on nodes that meet your security requirements, maybe specific OS hardening, network isolation, etc., and keeping it isolated from less trusted or potentially noisy neighbor workloads in the cluster.
Wow. Okay, that really was a comprehensive journey, starting inside Keycloak's config, moving through web security principles, and landing squarely in the infrastructure security concerns of the deployment environment, especially Kubernetes.
It really drives home the point, doesn't it? You absolutely cannot secure Keycloak by just tweaking settings within its admin console. It's a whole system, a defense-in-depth challenge.
Totally. Let's recap the layers we peeled back. Layer 1, Keycloak's own configuration. Getting those OAuth ADC flows right, nailing redirect URI validation, handling response modes securely, choosing the correct client types, public versus confidential, using strong client auth like signed JWTs with JWKS, applying least privilege via client scopes, securing user attributes and session timeouts, implementing robust MFA, and being incredibly careful with admin roles versus fine-grained permissions, plus securing tools like CLI.
Then layer 2, applying those general, fundamental application security principles. Things like input validation, even though Keycloak does a lot, your apps using it still need it. Setting security headers on web interfaces like referrer policy and content security policy. Insisting on TLS for all communication with no fallback allowed. Handling sensitive data with care, especially avoiding URLs for tokens or session IDs. And just solid password and key management practices across the board.
And finally, layer 3, securing the deployment environment itself, whether it's VMs or containers, but especially focusing on Kubernetes here. Implementing network segmentation with network policy, default deny, setting resource limits and quotas to prevent DOS and ensure stability, ensuring encryption at rest for sensitive config, and etc., using K8 secrets and config maps correctly and securely, drastically restricting container privileges with security contexts, non-root dropped caps, using immutable image digest for supply chain integrity, and ensuring secure node configurations and workload isolation using scheduling constraints.
It's definitely a complex picture. Weakness in one layer can potentially be mitigated somewhat by strengths in another, but real, robust security for something as critical as Keycloak requires paying serious attention to all three layers.
That was quite the deep dive into securing Keycloak, pulling from all these different valuable perspectives. Hopefully that gave you, our listener, a serious shortcut to feeling well-informed, maybe uncovering some surprising details, and definitely providing actionable insights drawn directly from this stack of source material.
Navigating all the security implications across Keycloak's features, general web standards like OAuth, and infrastructure platforms like Kubernetes can definitely feel overwhelming sometimes.
And here's where it gets, I think, really interesting. I keep thinking back to that OWASP ASVS mention of documented security decisions. I believe it was ASVS v5.0 level 2 requires this. It's not just doing security things, but documenting why you did them, tailoring your security posture to your specific needs and risks.
Yes, exactly. It's about moving from just implementing features to truly understanding and justifying your security choices.
So the question this leaves me with, for you listening, as you manage or deploy Keycloak, have you explicitly documented why you chose, say, a public client type over confidential for that one specific application? What was the reasoning? Why are these particular scopes granted to that client, and what risk does it mitigate or accept? Why did you configure your proxy TLS termination settings exactly the way you did?
Does that documentation capture the specific threats you were thinking about? Does it articulate the trade-offs you made? And crucially, does this documentation live and breathe? Does it evolve as your application landscape changes, as new threats emerge, or as Keycloak itself gets updated?
It really feels like the difference between just having a set of security configurations and having a truly justified, understood, and maintainable security posture for this absolutely critical piece of your infrastructure.
Something to definitely mull over.
Indeed. Something to think about as you continue your own deep dives. Thanks so much for joining us today.